Hello and welcome to this video session focused on Japanese Tansu Storage Chest. We'll look at an example, discuss the joinery options for this model, talk about the calculations, the design steps, and then go into some computer-assisted design. To begin with, what exactly is a Japanese Tansu Storage Chest? Here's a model of one. This model happens to be broken down into a carcass and the drawers. The example used in this session is not, of course, not the only type of Tansu chest. Here's another example. Many others can be found with a quick search on the internet. Several instances of joinery are used in this model. One, of course, are the drawers that slide in and out. Another are the joints that join the sides of the carcass to the tops, as well as this sliding dovetail that joins this panel to that top, and so forth, as well as the joints that join the sides of the drawers to the fronts of the drawers. Several variations of joints can be used to join the drawer sides to the front. The first we'll take a look at will be called dovetails. Probably obvious why they're called dovetails. If we take a look at this picture of a dovetail. One type of dovetail is called a through dovetail. It's called through because you can see both from the front as well as from the side. You can see the joints in both directions. A second type of dovetail is called a half blind. It's called half blind because if we look at it from the front, cannot see the joint. Look at it from the right, there it is. And so it's called half blind. Another variety of dovetails is called full blind. It's full blind because we cannot see it from the front or from the side. However, if we turn on the visibility of the hidden edges, you can see that they are actually still in there. Let's turn that back off. Changing the dovetail angle from 7.125 degrees to 0. Ends up with what are called box joints. Looking at the carcass from the front, zooming in a bit, we can see examples of sliding dovetails. They also have an angle to them, and they go usually from the front to the back. Some of them are stopped and have not just short of the front and back. These happen to go all the way through. Those typically are used in bookcases to hold the sides together a little better, mechanical advantage there. This session will focus mostly on full through dovetails, as shown in this example. The advantages are several. These are normally used in what we're showing here, attaching the side of a drawer to the front of a drawer so that when you pull on the drawer, maybe hundreds or thousands of times over the life of the drawer. The mechanical advantage here given by the fact of this trapezoidal shape helps to hold it together. Of course, their glue will also do that. The other parts of this will be the dimensions from one side to another. So we'll need to know the dimension going across here. Which appears to be 10.5. We need to know the distance of this half pin, one on each end. Which, if I can move those out a little bit. And it's showing here at 1/4 of an inch. A little hard, maybe a little hard to see. Also need to know how wide is each dovetail itself. In this case, 0.8313. Need to know how big is this gap from one dovetail to the next. In this case, it's 0.1875. And of course, what's the distance from the depth of the dovetail from here to here? In this case, 3/4 of an inch. From what's been shown so far, you can probably see that the various dovetails are very closely related, the similarities. In fact, changing one parameter did it for the whole model to change it from a through dovetail to a half blind to a full blind and also to a box joint, simply by changing one parameter in the model. As discussed, in order to draw or finally to cut these, we're going to need to know several pieces of information to lay out these dovetail joints. We talked about the board width, talked about the distance of the half pin on each end, the width of the dovetail itself, and how big is that gap from one dovetail to the next, and finally, how many dovetails do we want to fit across the board. An easy way to do the layout is to put that information into Excel and let it do the arithmetic for us. So the example that we just saw, the board was 10.5 inches wide, the half pin width was 1/4 of an inch, the pin widths were 0.1875, and we have 10 going across. Entering that formula into Excel, we get the dovetail width of 0.83125. Again, you can confirm that by looking back at our model here. And there it is. That's exactly what Excel showed us, minus a little bit of a rounding factor there. So we've done the calculations involving the layout of the dovetails across the board, but some other information is also needed, namely the number of board feet for each component, the cost, and the weight. Those are going to depend on several things. Here is a simple way to do that. This calculator is on the internet. You can calculate both the weight and the volume here. It asks you some questions. Is it treated? What species? And so forth. And you end up with a calculated weight and cost by first getting the board feet from that calculator, setting up a table for each species of wood. What is the mass per board feet or weight per board foot? What is the cost per board foot? Here we're going to use cherry and mahogany and maybe one other. Entering that information into our spreadsheet lets us calculate the board feet, the cost, and the mass for each species. These were used earlier to lay out the dovetails, but we need some more information, namely the slope. The slope of dovetails will vary depending on whether it's hardwood or softwood, depending on whether it's half blind or fully blind, depending also on whether it's a sliding dovetail or not. To calculate the angles for dovetails, it's not a whole lot different than doing the slope if you're building a roof or a bridge or something, anything with an incline. We start with what is the rise and what is the run. In other words, what is the vertical distance traveled? What is the horizontal distance traveled? If you know that, then Excel will calculate the degrees of an angle for you. Of course, rather than having Excel do the arithmetic for us, we could go back and do it the old-fashioned way. Take the board feet, which is the thickness times the width times the length times the quantity of each component. If the thickness, width, and length are in inches, we'll need to divide by 144 to come up with board feet. Once we have board feet, we can calculate the cost, which is just the number of board feet times the cost per board foot. Likewise, we can calculate the weight, which is the number of board feet times the pounds per board foot. So here we've done the math manually instead of letting Excel do it. Of course, that's a little more work, a little more error prone, but of course possible. We used Excel to calculate the dovetail width for us. You could also do this manually. Here's the formula. Here's an example of coming up with the dovetail width for this example. Could also calculate the angle in degrees using trigonometry, if you remember that from high school math. An easier way might be to use an online calculator. Here's an example of doing that. Again, we put the rise over the run, click calculate, and out comes the same number that we got out of Excel or when we did the arithmetic manually. Here's an example of letting our CAD package, let the computer design model help you in calculating these. So here I've created a circle, put in the rise over run, and out pops the same value that we got out of Excel or when we did the math manually. Here's an example of calculating angles using the unit circle. The unit circle has a radius of 1 because often we're dividing the opposite or the adjacent or whatever by this. So dividing by 1, which is this distance, becomes very easy. In this example, if we want to know the sine here, the sine of 30 degrees is, maybe we remember, is half of the length of the hypotenuse. If it's not 30 degrees we want, we could move this around to various angles and get whatever measurement we want. That avoids all of the arithmetic that we've just seen done earlier. How do we get from a concept where we want to design this model and eventually build it to this actual model? The steps that would normally go through would be to find a model, then tailor it, then actually create the model here in some CAD package, and then finally render it. The problem with that is very seldom would we be able to find a model that exactly matches what we want. Could start with a blank sheet of paper, but that makes it very difficult. So we search for one. There are lots of free ones on the internet. Download it, figure out how closely or not that it matches what our preferences are, and then we tailor it. Tailor it in terms of what materials, what kind of joinery we want to use and so forth, and then model it here in the package. Modeling, at least in this package, normally follows this pattern, the following pattern. First, we establish the component hierarchy. In this case, we see that the carcass is made up of panels, tops, shelves, and edging. Then we enter the parameters and formulas in here, the same things that we've seen in our manual calculations, and also the same ones that we've used in Excel. Then we create sketches and extrude these out into a 3D model. Each of the components then are joined together, which locks them in place relative to each other, and usually at least one is grounded so we can't move the entire model around. Once the model is drawn, then we start to render it. Several variations of that include Making 2D drawings, such as this drawing of the drawer. It's two-dimensional from the front, the right, the top. Here's another version. In this case, we've exploded out the detail here so we can actually see the dimensions of each detail. And here we let the package put the parts list in it here for us. We actually don't need that so much because it has the cutting list recorded in Excel, but it might be handy. Next, it's usual to explode this so we can see how things fit together. So let's animate this. Let's take this and go back to the beginning and watch it explode the sides of the front of the drawer out, just showing how these things fit together, the bottom and the sides and so forth. Could also take a look at the explosion of the carcass. So let's animate that. Send it back to the beginning and let it explode that out. Just gives a better picture of how things fit together. Of course, after going to all the trouble of creating this model, we would probably like to share it with others. There are a couple ways of doing that. If someone else happens to have the same CAD package or one that's compatible, of course you can export the design to various formats, or you can share it by looking at the details on the web. The advantage with doing that, of course, is it doesn't require someone else to own the same CAD package as you have, but they can take a look at it, make comments, suggest improvements without actually changing the model themselves. Just notify you of what they would really want to see. Another way is we've gone to the trouble of making those 2D drawings. Those drawings then, of course, can be exported to, in this case, PDF format. So here is the drawing with 4 pages from the front, the left, the exploded view, and so forth. Here's the drawer exploded, and all this with the dimensions on it. Makes it very handy for ourselves if we want to print these off and take them out to the shop to get the dimensions, or to email or put it on a shared drive someplace where whoever's going to build this thing can actually look up the drawing without necessarily having to print them. So to wrap up this session on Tansu Storage Chest, Japanese style, we've taken a look at what exactly is an example of a Tansu chest, the design approach and steps to go through the finding and tailoring and doing the calculations, finally modeling it in a CAD package, and then rendering it for our own use or for others to use or comment. We've covered the various types of joinery, specifically the joinery for dovetails, through, half blind, full blind, box joints, and sliding dovetails. Hopefully that all made sense, along with the calculations for doing cost and weight, and the angles for the dovetails, and the layout across the board for a dovetail. All of that was covered in this example. So next, here's a challenge. I'd like you to provide an alternative definition of a dovetail joint. Here's an example. Would like it to be humorous. Maybe this one is, maybe not. So how do you define a dovetail joint? A dovetail joint is a dive bar or a pub where doves gather to drink or socialize. Okay, maybe you can do better. A question then is, what should be done if a dovetail joint is not a perfect fit? Don't try this at home. This is my approach. My answer is try a bigger hammer. So thanks so much for watching. As always, please indicate what following sessions might be useful. Make constructive comments. They're always welcome. Please like and subscribe, or not. And finally, Tansu. Tansu very much. By the way, Elvis has left the building. I'm all shook up.